फर्स्ट ऑर्डर डिफरेंशियल इक्वेशंस चैप्टर 2 में एग्जैक्ट इक्वेशंस टॉपिक 2.4 एक्सरसाइज 2.4 हमने एग्जैक्ट इक्वेशन पढ़ लिए हैं कि एग्जैक्ट इक्वेशन क्या होते हैं। ऐसी इक्वेशन जो कि किसी फंक्शन का टोटल डेरिवेटिव हो जिसमें उसे एग्जैक्ट डिफरेंशियल इक्वेशन कहते हैं और हम उसको फाइंड किस तरीके से करते हैं कि एग्जैक्ट है। हम पार्शियल एम ओवर पार्शियल वाई करते हैं, अगर वो इक्वल हो जाए पार्शियल एन ओवर एक्स पार्शियल एक्स के तो हम कहते हैं कि एग्जैक्ट डिफरेंशियल इक्वेशन है। फिर इसको सॉल्व करते हैं। टॉपिक में आपको बता चुकी हूँ, आप उसकी वीडियो देख लीजिएगा एग्जैक्ट डिफरेंशियल इक्वेशन की। यहाँ पे हम सिर्फ एक्सरसाइज 2.4 कर रहे हैं। 1 से 24 क्वेश्चन में डिटरमिन वेदर द गिवन इक्वेशन इज एग्जैक्ट, इफ इट इज एग्जैक्ट सॉल्व इट। क्वेश्चन नंबर 5 है, ये आपको डिफरेंशियल इक्वेशन दी हुई है, हमने चेक करना है कि एग्जैक्ट है कि नहीं। dx के कोफिशिएंट को हम mxy कह देते हैं, dy के कोफिशिएंट को हम nxy कह देते हैं। mxy मीन्स फंक्शन ऑफ m is function of x and y, here n is function of x and y. Now we will, अब हम क्या करेंगे, अब हम mxy को जो है पार्शली डिफरेंशिएट करेंगे विथ रिस्पेक्ट टू y। ये हमारे पास एग्जैक्ट डिफरेंशियल इक्वेशन का क्राइटेरिया है। वी आर partially differentiating the function m with respect to y. Here x and the constants real numbers are constant when we partially differentiate with respect to y. So 2 and x are constant and the derivative of y square is 2y. Here minus 3 is also constant, so its derivative is 0. So we get 2 into 2 4xy. Now partially differentiate n with respect to x. 2 and y are coefficient and the derivative of x square is 2x and the derivative of 4 is 0. So we get 4xy. Here partial m over partial y is equal to partial n over partial x. So the equation 1 is exact differential equation. This means there exists a function f of xy such that f sub x is equal to this and f sub y is equal to this. When it is an exact differential equation, then there exists a function f whose total differential is partial f over partial x dx partial f over partial y dy is equal to 0. If we consider the function f of xy is equal to c. So the solution of this exact differential equation will be f of xy is equal to c and its exact differential is this. By f sub x we mean partial f over partial x and partial f over partial y by f sub y. So if we compare this exact differential with our exact differential equation, then f sub x is is equal to this function and f sub y, which is a coefficient of dy, is equal to 2y square plus 4. Now from we called it equation 2 and equation 3. From equation 2 or equation 3 we can find f by integrating equation 2 with respect to x and integrating equation 3 with respect to y. So we can choose which equation we want to take depending upon whose integration is simple. So I am taking equation number 2 and integrating it with respect to x. So the derivative and integral will cancel and we get f, and here we are integrating it with respect to x, so 2y square is coefficient. Now integral of x is x square by 2 minus 3 integral of 1 is x plus constant of integration. So here constant of integration is a function of y. By simplifying the equation we get x square y square minus 3x plus h of y. Now we have equation 3 in which we have f sub y. So we can compare it with equation 4 to get the value of hy, which is unknown here. So we partially differentiate equation 4 with respect to y. So here we get f sub y, and here x square is coefficient, so the derivative of y square is 2y minus 3x. Derivative of minus 3x is 0 with respect to y, and derivative of h of y is h prime y. Now it is equal to equation number 3. So here we get the value of h prime y, which is 4. Now integrate this equation with respect to y. Integrate this equation with respect to y, and we get, here we get the derivative cancel with the integration, and we get h of y, and here the 4 is coefficient, and integral of 1 is 4y. We didn't write a constant of integration here because we will write in general solution. If you want to add here c or c1, then it's okay. Now we get the value of h of y, then we put it in equation 4. So f is equal to x square plus x square y square minus 3x plus 4y. And the solution, as I said, the solution of this differential equation is f of xy is equal to c. So the solution is f of xy is equal to c. I hope you understand this question. Now question number 17. Question number 17. First of all, we will put this differential equation in standard form. So we multiply it by dy. So we get this form. Now the coefficient of dx is mxy. Suppose coefficient of dx is mxy and coefficient of dy is nxy. Then we partially differentiate m with respect to y. X square is coefficient, and the derivative of y cube is 3y square. This function all depends on x, so its derivative is 0 with respect to y. Now partially differentiate n with respect to x. Y square is coefficient, and derivative of x cube is 3x square. So m sub y is equal to n sub x. So equation number 1. So equation number 1 is exact equation, exact differential equation. So there exists a function f of x by such that f sub x is equal to this and f sub y is equal to this. We called it equation. Okay, as I have already written equation 1 here, so I am removing it. We called this equation 1 and this equation 2. Now integrate equation 2 because it's simpler than equation 1. So integrate equation 2 with respect to y. The derivative and integration is cancelled, and now integrating this with respect to y. X cube is coefficient, and integral of y square is y cube over 3 plus integration of constant of integration, which is function of x. Now to compare it with equation 1, we have to partially differentiate equation number 3 with respect to x. So it will become f sub x, y cube over 3 is constant, and derivative of x cube is 3x square. Now derivative of h of x with respect to x is h prime x, and f sub x uh, comparing it with equation number 1, we get f sub x is equal to this. Now we can find the value of h prime x from here. These two terms cancel out and we get h prime x is equal to minus 1 over 1 plus 9x square. To get a value of h, we integrate it with respect to x. Integrate it with respect to x on both sides. Minus can come out of integration side. Now integral and derivative cancel and we get hx, and now integrate 1 over 1 plus 3x whole square. With respect to x, we get tan inverse 3x divided by 3. Now we put the value of h in equation number 3 to get the function f of xy. So f of xy is this. The solution of the differential equation is f of xy is equal to c. So f of xy is equal to c. To remove the denominator, we multiply it by 3 and we get 3c. We call 3c another parameter c1. So it's the general solution of equation number 17. Now question number 27. Solve the given differential equation subject to the indicated initial condition. This is the given differential equation we called is 1, and there is also a condition which is the initial condition. Here y is 2 and x is minus 1. So we will solve it by the same method as I described earlier, and when we get the general solution, we will put this initial condition. So we call this coefficient of x as m xy and coefficient of dy as nxy, and then partially differentiate m with respect to y and n with respect to x, and when these are equal, then we can say equation number 1 is exact differential equation. Then there exists a function such that f sub x is equal to this and f sub y is equal to this, and then we taking one equation, equation 2 or 3, and integrate. If we take equation 2, then we integrate with respect to x. If we take equation 3, then we integrate with respect to y. So I take equation 2 and integrate with respect to x and get this equation in which hy is constant of integration. And then to compare it with equation 3, I partially differentiate it with respect to y and then compare it with equation 3 to get the value of h prime y, and then integrate it with respect to y to get the value of h. Then I put it in equation 4 to get the function f, and the general solution is f of xy is equal to c. Now this is the general solution, and we will put the value of x is equal to minus 1 and y is equal to 2 in this equation, so that we get the value of c is equal to 8. Now put the value of 8 in this general solution and we get the this is the solution of the initial value problem, which is also a particular solution of this differential equation. In problems 31 to 34, find the value of k so that the given differential equation is exact. So you can see that this differential equation, the value of k is unknown. So we assume that it is exact differential equation and we will find the value of k. So going in the similar way, the coefficient of dx is, suppose the coefficient of dx is mxy and the coefficient of dy is nxy, and since the equation is exact, that therefore my should be equal to nx. So n sub x means partially differentiate n with respect to x, we get 3y square is coefficient and the derivative of x is 1 with respect to x. Here 20y cube is coefficient and the derivative of x square is 2x. So we get 3y square plus 40xy cube. Now as it is exact differential equation, so it must be equal to my, and m partially differentiating m with respect to y, we get 3y square plus kx 4y cube. So as these two equations are equal, so we solve this and get the value of k is equal to 10. Question number 35. Determine a function mxy so that the following differential equation is exact. Here the mxy is unknown. So we will find the value of mxy. What is the function uh, mxy which make this differential equation an exact differential equation? So nxy is this, and we know that the if we if it is exact differential equation, then there must be a function f such that coefficient of m is fx and coefficient of dy is fy. So here fy is also equal to this function. So we try to find f from this. So integrate it with respect to y, integrating both sides with respect to y. Derivative and integral cancel out and we get f. Here we can apply the linear property of integration, and the integration goes term by term, and uh, here we are integrating with respect to y, so x is coefficient, so it remains here, and e raised to power xy, integral of e raised to power xy is e raised to power xy divided by derivative of xy with respect to y, which is x. So x cancel, we get e raised to power xy. Here 2 and x are coefficient, and integral of y is y square by 2. 2 to cancel, we get xy square, and 1 over x is coefficient, and integral of 1 is y, plus h of x is constant of integration with respect to y. So we know that m is partial f over partial x. So we differentiate this equation partially with respect to x. We get e raised power xy, and then partially derivative of x of xy with respect to x. So we get y. Here partial derivative with respect to x is 1 and y square is coefficient. Here y is coefficient, and partial derivative if we take x above, it become x inverse. So partial derivative of x inverse is x in minus x minus 2, and partial derivative of hx with respect to x is x prime x h prime x. So h prime x, we may take h prime x is equal to 0, and the m is this function. So if we take m is this function, then this differential equation will become exact differential equation. Now the question number 39 is not an exact differential equation. You can see from here that if you take this m and partially differentiate it with respect to y, and take this n and partially differentiate with respect to x, then they are not equal. It is also written in question, it is sometimes possible to transform a non-exact differential equation into an exact equation by multiplying by a function which is called integrating factor. Solve the given equation by verifying that the indicated function is an integrating factor. So here the integrating factor is xy. As this is not exact differential equation, we will multiply it by integrating factor. So here it become x square y square, here it become xy square, and here it become x square y is equal to 0. Now mxy is this and nxy is this function. Now we partially differentiate m with respect to y, and we get minus x square is coefficient, and with respect to y is 2y, and sin x is coefficient. Now here 2x cos x are all coefficient, and derivative of y square is 2y. Now here now we integrate differentiate, partially differentiate n with respect to x. We have two function of x, 2y y is coefficient, and we have two function of x which is x square and cos x. 2y is coefficient, and we have x square and cos x. So we will apply a product rule. First we differentiate x square, we get 2x, and cos x is written, and now we differentiate cos x and we write x square, and derivative of cos x is minus sin x, and then we multiply it and we get the same function. So my is equal to nx. So it is this differential equation is exact differential equation, and we can find a function f such that f of x is equal, f sub x is this and f sub y is this. Now equation number 2 is simple, so we integrate it with respect to y, and we get f is equal to 2x square, and cos x is coefficient, integral of y with respect to y is y square by 2, and we get this, and constant of integration is function of hx. Now to compare it with equation 1, we partially differentiate it with respect to x, it become f sub x, y square is coefficient. Now we again get x square cos x, we will use integration by we will use uh, product rule for differentiation. So first derivative of x square is 2x, cos is written the same way, and then y square x square is written in the same way, and derivative of cos x is minus sin x, and derivative of hx with respect to x is h prime x. Then we equate this equation, compare this equation with equation 1, and we find the value of h prime x, which these two terms cancel out with these two terms, and we get h prime x is equal to 0. So we integrate it with respect to x because it's a function of x, so we integrate both sides with respect to x, and derivative and integral cancel out, and we get h of x, and integral of 0 with respect to x is constant. So we get we put this value in equation number 3, and we get f is equal to x square y square cos x plus c. So the general solution is, as it's already contains c, so general solution is f of xy is equal to 0.